So we now have the complete solutions for the particle in a box. We know that the wave functions, the eigenfunctions of our system are given by this set of equations, right? Sine n pi x over a with the normalization constant square root of 2 over a in front. And we know the energies of the system, E equals n squared h squared over 8m a squared. And so we've solved the Schrodinger equation. This is what we do in quantum mechanics. Now the question becomes, how is this useful? What can this information provide for us? And so let's go through, I'll talk in general terms first in this video about what sort of questions we can now answer because we have this information. And then in some other videos, we'll go through some specific examples of doing this, where we have some integrals to solve and things like that. So question number one that we can answer is, where is the particle? Well, at least we can give a probability. So, for example, you may ask, what's the chance that the particle is on the left-hand side of the box? All right, and so what we can think about is how do we define that mathematically? So we now have a probability distribution. We can take our wave functions, psi star psi, and if we want to find where the particle is, we can integrate. Say, if we want the left-hand side of the box, that would be from 0 up to a over 2. And if we solve this integral, that tells us the probability that the particle is in the left-hand side of the box. Now we could change the limits on this integral to anything we want. We can make it, what's the chance it's in the middle third of the box, or, whatever else we come up with. So this gives us a way to find probabilities of finding the particle in a specific place. And what we'll see is that what we get from quantum mechanics is different than what we get from classical mechanics in certain cases. So for the lowest energy state, for example, you're more likely to find the particle in the middle of the box than on the edges. Classically speaking, that makes no sense. You'd expect to find an equal distribution throughout the entire box, classically speaking. And the other thing is that we'll come up with specific points in the box where you won't expect to find the particle at all. We call these nodes. All right, so that's one example of a question we can answer. Another question we can answer is we can find average values for things that we can observe about the system. So for example, and this is we'll introduce this idea of what's called an expectation value. We'll talk about this more in the next chapter as we go over the postulates of quantum mechanics in general, but if we have some observable S, so some property of the system that we can observe, if we want the expectation value or the average we expect, the expectation value is given by the integral of our wave function, whatever specific wave function, of the S operator d tau. Okay, so this is our operator that corresponds to S. So say this could be the position operator, the momentum operator, the energy operator, which is the Hamiltonian. And this d tau over here, this represents, all space. So whatever variables we're considering. In our case, so far we've only talked about x, but we could have, say, x, y, and z, or this could represent, angular coordinates, polar coordinates, which we'll look at later as well. And so we'll go through an example of, what is the average momentum of the particle in the box. That'll be a separate video. Okay, so that's the second thing we can look at specifically. Something else that we can look at is energy spacings. This is our third sort of concrete thing we can get from the values that we have. So we have, what is the description of the energy spacings? And so what that can tell us is how much energy does it take to, say, take an electron in our particle in a box up to a higher energy level, or if it's in an excited state, how much energy will it release when it goes down? And so this is going to be directly related to things that we can observe, right? So this is going to be directly related to the spectroscopy of the system. And so we'll actually use these energy spacings to look at conjugated carbon chains and see how well we can match the predictions of the particle in a box to what we actually observe for the the light that's absorbed by dye molecules that have this sort of structure. One of the other things that we can do is look at uncertainties. And so when we have the expectation values, the uncertainties, in the sense of the uncertainty principle, right? How well do we know these values? The variance in a given observable, say x, is given by the expectation value of x squared minus the expectation value of x squared. And so we could say sigma x is the square root of this what we'd call the standard deviation. So if we have the wave functions, we can find these expectation values and we can find the uncertainties. And again, we'll go through this in more detail in a separate video looking at a specific example for, say, x and for the position and the momentum. All right, and so those are the sort of questions we can answer once we have the wave functions, the eigenfunctions, and also know the eigenvalues for the energies. And we'll have a set of videos kind of going through each one of these, looking at some specific details.